Welcome to DAC 56. My name is Krzysztof Szczur. I'm Hardware Verification Products Manager, and I'm very excited to show you the new demo of using the ALDEC HES-DVM platform for hardware-software co-verification in the hybrid co-emulation environment. Enabling early hardware-software co-verification is important for today complex system-on-chip designs that require both hardware and software verification. Proper platform that enables this hardware-software co-verification should contain an accurate model of the processor as well as the platform to implement several custom peripherals. ALDEC provides such a model to verify hardware and software for ARM-based system-on-chips, and that hardware platform is composed of our product lines. As you can see here in this slide, we have the hardware setup, which is composed of the large FPGA board, which is the ALDEC HES board, with Xilinx UltraSCALE 440 FPGA, and the smaller board, which is based on Xilinx Zynq MPSoC with the Zynq UltraSCALE Plus FPGA and ARM that contains also the ARM processor. So they are connected with the host-to-host bridge daughter card, and also there is a IP that implements the bridge to take the AXI bus from the ARM processor and make it available in the large FPGA. So in this platform, you can actually model precisely the hardware platform for the ARM-based SoC, and the ARM Cortex components from the SoC can be mapped to the Tyson board with the Zynq FPGA, whereas the remaining part of the project can be mapped to UltraSCALE FPGA on the big board. This way, we resolve the common limitation of the Zynq platform, which is the limited number of FPGA capacity. So we extend the FPGA capacity to very large FPGAs, and we also have multi FPGA boards that can be used in the same way. So this platform has several benefits. So first of all, when you use this kind of platform, you have 100% accurate hardware model of ARM processors. In the Tyson board, in the Xilinx Zynq FPGA, there is quad-core ARM Cortex A53. There is also dual-core Cortex R5, and also the GPU, which is also embedded in the Zynq FPGA. Then what we provide is the easy connection of the ARM hardware model with the AMBA AXI bus. So we provide a ready-to-use bridge between the Zynq FPGA and the large UltraSCALE that provides AMBA AXI connection. So you can easily split your SoC into these two devices. On the Tyson board, except of the Zynq FPGA, we have several peripherals that include a DDR4 memory, Ethernet, USB, HDMI, and many more. You can even extend it with some FMC daughter cards. What's the benefit of using like predefined ARM processors? Well, there is no need for the ARM CPU RTL code for ARM processor to be able to emulate your project. And the second, even if you have the RTL code, you don't need to implement it in the UltraSCALE FPGAs. So more FPGA resources are left for your other custom components. Another very important property of this solution is that you achieve the prototyping level clock rates for ARM CPU subsystems. So the ARM processors can run as fast as 1.5 GHz, whereas the remaining part of your design can run at emulation speed, giving you the comprehensive debugging features and opportunity to analyze some complex problems or corner case bugs in your project. So let me demonstrate how that solution works. So I will show you the live demo of that solution, and the block diagram of the design that we implement to demonstrate this solution is shown in this slide. So very briefly, let me explain what components we have here. On the left side, you can see ARM processor subsystem, which is implemented into the Tyson board in the Zynq UltraSCALE Plus. That basically shares the exports the ARM Cortex CPU to the other board, which is the emulation board. In between these two boards, we have the ALDEC AXI to Aurora component, which is the bridge that exports the AXI bus to the UltraSCALE US440 FPGA. In US440, we have design under test, and also we have some transactors. Transactors are the components that enable connection with the host computer, and in the host computer you can develop a test bench, which is a transaction level test bench that communicates with your design. So this kind of environment is a hybrid emulation environment that enables both running the CPU subsystem at very high speed and remaining part of your design at the emulation speed. And there is also a interconnect module, which is the AXI network on chip component that enables clock domain crossing between the fast clocks of the ARM processor and the slower clocks of the emulation domain. So in this environment, we can demonstrate that we can transfer data from ARM processor to the emulation domain, to the design under test, and to some transactors, and vice versa. We can also transfer data from the AXI transactors to the ARM subsystem domain and to the DDR memory, which is one of the peripheral connected to the ARM core. Okay, so let me demonstrate you how that platform works in practice and what you can achieve here. So what you see on my screen is the Xilinx SDK software that's used to drive the debugging process for the ARM Cortex processor. Then you also can see two Linux terminals. The upper Linux terminal will be used to run the emulation test bench. So I have the script which runs this test bench, and I will start the script right now to enable the emulation. This starts the emulation test bench, which runs on this host computer, and it connects with the AXI master and slave transactors, which you have seen on the block diagram. So the emulation part is the one part of the design that connects with the Xilinx UltraSCALE FPGA and the peripheral DUT, which is implemented in this FPGA. On the bottom, I have another terminal, a Linux terminal, which runs a Minicom software, which is a serial port terminal. So on the hardware platform, I have a connection from the Zynq FPGA to the serial port, and this will be used just to see the messages which are printed from the ARM processor. So this is my whole environment. So I have the visibility into the ARM processor from the SDK debugger and from the Minicom terminal, as well as I have also visibility into the emulation side and the emulation test bench from the upper terminal. So right now I started the emulation, and as you can see, the emulation test bench, it tries to read some registers. These are the registers inside the Aurora AXI bridge that indicate whether we have synchronized the two hardware components, the ARM part in the Tyson board and the US440 which connect together. So we need this kind of synchronization because the link, the bridge, AXI bridge, it uses the GTX lines, and we need both boards to be configured in order to work properly. So right now I started just emulation test bench, and the Tyson part is not running yet. That's why we still get the configuration and the status register that indicates that there is no proper synchronization. So now, using Xilinx SDK, I can configure the Zynq FPGA with the bit file and upload the software that I'm going to debug in this platform. So I will hit the debug button that compiles the software and also gets the FPGA bit file and uploads to the FPGA. So that will take a few seconds because the uploading FPGA bit file is done using the JTAG cable. And after the FPGA is programmed, we can see the change in the status register. Okay, so as you can see, after programming the FPGA, we immediately see the change in the status register. And now the status register indicates that both the Tyson board and the HES board are configured, and the link, the GTX link, which bridges the AXI bus, is synchronized and ready to use. So right after this detection of both sides, the test bench executes the first test. It's a simple loopback test between the transactors, and after that it enters the loop waiting for the ARM processor. So in order to receive the indication from the ARM processor, we have to switch to the Xilinx SDK, and we need to run that program in the ARM processor that will send proper handshake data from one board to the other. So as you can see, in Xilinx SDK we can debug our embedded software as usually. Software designers are very familiar with this environment, so stepping through the code is possible here. Also, please notice that when we have some print functions calls, the effect of the result of the print is printed here in the Minicom terminal. So I will step through the lines of code. I can also set up some breakpoints. So I can step through the code. I can run the code until the breakpoint, and these are the normal software debugging activities. So right now, when I execute the send ARM ready function, it will send the message to the other side of to the emulation side of my design, and that should be captured by my emulation test bench. So let's enter this function and see what happens. So as you can see in this line, we are going to send the F00 FADE word to hardware, and that should be captured and received on the emulation side. So let's execute this line. And indeed, you can see that we received the same data on the emulation side. So that proves that you can transfer data from the ARM Cortex to the emulation side. But what else you can do? You can also transfer data from the emulation side to Tyson board. So the AXI master can be on both sides, on the Tyson board, which is the ARM Cortex, as well as on the emulation side, where you can implement either the master transactor or other master devices. So as you can see, right after receiving the ARM handshake, the second test was initiated by the test bench, And this is the test of writing data from emulation site to Tyson board, where we have the DDR memory and we save data to the DDR memory. So this test passed as well. And then we wait for the end of test. So the emulation test bench is done. We're waiting for another synchronization from the ARM side. But before we do this, we can execute another tests from the ARM software. So let me execute a few more lines of the code to show you that there are some other tests which are running, and these are initiated from the ARM core side. So the first one is testing if in the DDR memory we have the proper data that we received from the emulation side. So let me step through this, and this test is passed as well. Next test is that we will send the data from ARM Cortex to the DUT which is in emulation. In the DUT we have one block RAM memory, so we will transfer data to this memory, and we'll read back this memory data again and compare whether the memory is correct. So I will execute this test, and as you can see, this test has passed as well. Similarly, I can send data to the transactor, to the slave transactor in the emulation side, and as you can see, the third test has passed also. So at the end, I will send another handshake message from the ARM core to the emulation side, and this handshake message indicates that we wish to finish the test, and then it will be again received at the emulation side, and the test will finish automatically. Okay, so the test has been finished. That concludes my presentation, in which you were able to see that the hybrid co-emulation platform can be very efficiently used for hardware-software co-verification and co-debugging. For more information, please go to Aldec website, www.aldec.com.